Hello and welcome back to our dependability module. So we have seen that there do exist codes that not only can detect errors but can also correct them. But the example that we have shown is not a very practical one because it has a lot of overhead. In order to encode what was worth 1 bit of information, we used 3 bits, so we had 200% overhead there. The trick here and the science is how to design these codes such that we get the desired coverage with minimum amount of overhead. And desired coverage here is SECDET, single error detection, single error correction with double error detection. So Hamming came up with those codes as well. And here is how it goes. We will start with data bits that are the result of our calculation. And we are going to interleave parity bits with those data bits to form the code word that we're going to store in the memory. In this case, there is a particular algorithm how they are being put together. So here is how an interleaving works. On top of this table here, we have bit positions of the code words that are going to be stored in the memory. 1, 2, 3, 4, 5, and so on. And then below that, encoded data bits are sitting at particular bit positions. D1 is at position 3, D5 is at position, D2 is at position 5, D3 is at position 6, and so on. And these other bit positions are occupied by the parity bits, P1, P2, P4, P8, P16. And this is done in a particular way such that parity bits are essentially always at bit positions that correspond to powers of 2. So these are bit positions that in binary correspond to 1, 1, 0, 1, 0, 0. Relatively easy to remember. But then on the bottom here in this table is shown which data bits are covered by which particular parity bit. So the first parity bit, P1, covers all positions that have an LSB equal to 1. So all odd bits are covered by the first parity bit. So if we include the P1 in that position, it is going to also cover itself and produce an even parity. So essentially every other bit is included in the first parity. What does it mean included? These are basically inputs in an XOR gate that are generating P1. P2 covers all bit positions that have the bit that is next to the least significant one equal to 1. So these are essentially pairs of these pink fields that correspond, D1, D3 and 4, and so on. And then P3 covers groups of 4, and so on. And this can continue indefinitely, but in practice we generally do this for a block. So if you have a data word that is 8 bits wide, we would add 4 parity bits to encode it. Let's take a look at an example of how we actually do that. So we are going to generate these parity bits to create even parity for each group. Let's say that we would like to encode a byte of data. There are 8 bits in this word here. So we are going to create a coded word by placing the data bits where they should be, and then we leave those spaces for our calculated parity bits. So these parity bits should be placed in their appropriate bit positions. So the first parity bit goes into bit position 1. So let's calculate and let's go through that example. So position 1 is going to be checking bits 1, 3, 5, 7, 9, and 11. So we are going to mark those bits in yellow and count how many ones are there. 1, 2, 3, 4. Therefore, in order to make even parity, that parity bit should be equal to 0. In position 2, it is going to be checking pairs of bit 2, 3, 6, 7, 10, 11. How many ones are there? There are 3, therefore in order to make it even parity, we should make this question mark equal to 1. Then we take a look at position 4 checks, mark up appropriate bits. We have only one among the yellow bits, therefore that should be also equal to 1. And finally, for position 8 checks, we have the last 4 bits that participate in that XOR. There are 2 ones among them, therefore this question mark should be equal to 0. All right, so this is our final code word. It consists of the data word and the parity checks. But let's, don't look at the correct answer. Let's suppose we receive something and we would like to decode if the word is correct, and if it is not correct, we would like to correct it. So suppose we receive this. We will map it to appropriate bit positions, and we'll find out that the bit 0, 1 in the first 2 bit positions are parity bits. There is another one over here. There is a parity bit P4, and finally there is a parity bit P8 at the bit position 8. The rest are the data bits. Let's figure out if the word is correct. So we receive this, and we are going to run the parity checks. Well, for the first parity check, we are going to figure out all the bits that, parity bit and the data bits that correspond in that check. The number is even, so it's good, it passes. The second one has the P2 parity has 1, 2, 3, 4, 5 ones, so it's not good, it's not correct. That one does have an error. Then we are going to check the bit P4. It has 2 ones in that check, so that is going to be correct. That check is going to be fine. And finally, P8 bit is in error because it has 3 ones. And then there is a very simple way how we calculated which bit position is the error, and you can work out the algebra. It's very simple, it's very elegant. This implies that the bit position is equal to the sum of the 2 parity bits, P2 and P8, so the error is going to be in the bit position 10. What should we do to fix that? We just go ahead and flip that incorrect bit, turn it into a 0. Then we decode this to make sure that it is correct. Miraculously, all the checks are satisfied and we have decoded the correct word. Very well. Now, what should we do if we have to deal with systems that can have more than 1 bit in error? So if you look at high-end microprocessors, they typically use SegDed codes, single error correction, double error detection. But some of the server processors that are working with more valuable workloads are going to have protection for to perform correction on 2 bits. So there is a different type of a Hamming code that is called double error detection, triple error detection, or DECTED. We're not going to go into it. And there are plenty of references of that. But generally, when we work with something that is noisier than microprocessors, like sending data over Wi-Fi or network transmissions and so on, we are going to see a lot more errors. And these errors are often going to be bursty, and we're going to see different ways how redundancy is added. There are generally things that we're going to encounter there, like cyclic error correction, forward error correction, and things like interleaving to break up these patterns and attack them with codes that can cover fewer errors. But that's way past the content of this course. That is it. This is all what we are going to cover here regarding correction of soft errors. And that is typically something that we're going to do in the memory. We're going to see a different view of redundancy just after a quick break.